Hello class, I hope you're having a wonderful day. Today I would like to take a look at another practice problem from chapter 6 with uniform circular motion. So let's go ahead and get started. A car racing on a flat track travels at 22 meters per second around a curve with a 56 meter radius. Calculate the car's centripetal acceleration. What is the minimum coefficient of static friction between the tires and the road is necessary for the car to round the corner without slipping? So let's first generate a column of knowns and unknowns. We know that the velocity of the car is 22 meters per second, and the radius of the curve is 56 meters. The problem wants us to calculate the centripetal acceleration identified by A sub C, and then what is the minimum coefficient of static friction? So mu sub S for static friction. So the first thing we can do is calculate the centripetal acceleration. We know that the centripetal acceleration is equal to the velocity squared divided by the radius of the curve. So the velocity is 22 meters per second, and we're required to square this divided by the radius of 56 meters. So let's take out our calculator. According to the order of operations, we're required to square the numerator first. So 22 squared is 484. Not only are we squaring the numerical value, we are required to square the unit value, so this is going to be meters squared per second squared. And in our denominator, we have 56 meters, so let's divide this by 56. This gives us 8.64. Now let's take a look at the units on centripetal acceleration. In my numerator, I have meters squared per second squared. We're dividing this by meters, which algebraically is meters over 1. So when we divide fractions, it's like multiplying by the inverse of the denominator. So this is going to be 1 over meters. As you can see here, one of our meters is going to cancel, leaving us with meters per second squared. So for centripetal acceleration, we have 8.64 meters per second squared. Okay, so now we need to calculate the static coefficient of friction. Okay, so we know mu sub S is equal to the static friction force divided by the normal force applied to the object. Okay, so static friction force is going to be the mass times the centripetal acceleration, because we know that the net force applied to this object is the vector is pointing to the center of the circle, and the agent of force is the static friction force. And we're going to divide this by the normal force. Now, if I drew a free body diagram here, we know that the weight force vector points in a negative y direction, and the normal force vector points in the positive y direction. And we know that there's no acceleration in the y direction, so we have an interaction pair. Our forces are equal in magnitude but opposite in direction. Okay, so we know the force of gravity is equal to mass times the acceleration due to gravity, and the value is negative for g because it's a vector and is pointing in the negative y direction. Normal force, though, is pointing in a positive y direction, so we know that this value will be positive. Okay, so mass times the acceleration due to gravity. Now, one thing I want to point out in this problem is it kind of gives us a hint, going around the curve without slipping. So when you have friction between a rolling tire and the road, this is static friction force, okay? It's not kinetic, because when that object rolls, it just touches the ground and then rolls away from it. The tire continues to rotate. Remember that kinetic friction means that there is sliding between two objects. So for example, when the objects are sliding across each other, there is kinetic friction. But in this case, it's a tire that is rolling, so that's static friction. And we know that static friction is greater than kinetic friction. But you might ask, well, that seems pretty weird when it comes to a tire rolling on the pavement. But let's think about this. Let's think about if you're in your car and you're driving and you slam on your brakes and your car goes into a skid. So your tires are stopped, but the tires are sliding across the pavement, okay? Well, that is kinetic friction force, because there's a sliding motion. But you cannot turn. See, kinetic friction force is less than static friction force. So you can't turn because there's not enough friction force. But if you're not braking, you can easily turn your steering wheel and your car will turn any direction that you're turning your steering wheel, because there's a greater amount of friction between your tires and the pavement. Okay, so back to the equation here. Sorry for that little tangent, but force of static friction. So in my numerator, I have mass and centripetal acceleration, which you've already calculated at 8.64 meters per second squared. In my denominator, normal force is the product of the object's mass and gravity. And remember, we're using a positive value because our vector's pointing up, so we must show direction since it's a vector. Now, looking at this, we have mass in the numerator and mass in the denominator. So those can cancel. My centripetal acceleration, once again, we're using our calculated value, 8.64 meters per second squared. And we're dividing this by the acceleration due to gravity, but remember, the vector points up, so 9.8 meters per second squared. Okay, so 8.64 divided by 9.8, we know the value will be less than 1, and we get the static coefficient of friction is 0.882, and it's unitless. Meters per second squared cancels with meters per second squared. So the minimum coefficient of static friction between this race car's tires and the road is 0.882. So I hope this has helped you out. If you have any questions, please let me know. Feel free to give me a call or send me an email. I would love to help you out. I hope you have a great day.